Hello class, this is day 27 assignment, building basic covalent bonds. It was assigned Thursday, March the 5th. It's due March the 10th, and this is the solutions video for that. So the first part of this video deals with ionic bonds, so you can compare and contrast them with covalent bonds. So let's go ahead and start this. So we're going to put two elements together, a metal and a non-metal. That's what's required for an ionic bond. So we have rubidium, and rubidium shows up. So you should have your periodic table. You should also have your 60 ion sheet and also your periodic table of charge numbers of ions. Rubidium shows up right here in the first column, so it has a +1 charge number. It wants to lose 1 electron to become like the nearest noble gas, which for it would be krypton. And oxygen has a 2- because it wants to gain 2 electrons, 1, 2, to be like its nearest noble gas, which is neon. So this is going to have a formula of Rb2O. This has a 1+, and you need 2 of those to balance with the 2- of oxygen. It asks you for the compound name, so let's go ahead and give that. It's rubidium. So the name of the cation does not change. The name of the anion, and the anion always comes second, is you just change the ending to IDE. So anything with oxygen would be oxide, rubidium oxide. Okay, let's go on to the next one. There's different compounds you can form from iron because it has a +2 and a +3, or 2+, I should say. We're going to start doing that more accurately, and a 3+. And bromine is a 1-. So it doesn't matter which one, we just choose one. So that's going to be Fe, and we'll choose the 2+. So we'll choose this one. And we're going to need 2 of these to balance with that. So it's FeBr2. 2 negative ones to balance with the 2+. If we'd chosen this, we would have needed three of the bromines. Okay, so that's iron. Since it has more than one possible charge number, you have to specify with a Roman numeral. Iron 2 bromide. Change bromine to bromide. Okay, there you go. And we move on to sodium nitride, and sodium has a 1+, and nitrogen has a 3+. We come over to our periodic table. There's sodium. There's nitrogen. It wants to gain 1, 2, 3 electrons to be like neon. So, and I said plus. That's incorrect. It's an anion, so it's a negative. 3-. So you're going to need 3 sodiums to match up with that 1 nitrate. Okay, and that's going to be sodium nitride. Just change nitrogen and add an IDE at the end right there. Magnesium and chlorine. Magnesium right here is a +2. It wants to lose 2 electrons to be like neon. And chlorine is right here. It wants to gain 1 electron to be like argon. So this is going to be a 2+, a 1-. That's going to be Mg. And then you're going to need 2 of these chlorines to match up with that. So it's MgCl2, and it's magnesium chloride, IDE. Next up is gold oxide. So you look at gold on your charge sheet. In transition metals, you have to look on either this or the 60 ions because many of them have more than one charge. Gold can either be a 1+ or a 3+. Let's go ahead and make it a 3+. You can choose on this one. So it's going to lose 3 electrons. Oxygen is always going to want to gain 2 electrons. So now what we have to do is switch this over here and this over here. and that gives you Au2. So 2 times 3 gives us 6, O3. Negative 2 times 3 gives us negative 6. So you have negative 6 on this side, positive 6 on this side, so they balance out, 6 and 6. All right, so that's going to be called gold. And we needed to use the 3+ charge. We chose to use the 3+ charge. So it's gold, 3, Roman numeral, oxide. Next up, okay, and next up is lithium, Lu. But I just noticed, there it is right there, number 71 on the periodic table. But I noticed it's not on your ion charge sheet, so I'm going to skip this problem and move on. I could change it to something else. Let's just skip this, okay? I'm going to line through that. All right. Okay, next up is osmium sulfide. So come to our sheet here, and osmium only has one charge. It's a 4+, so that's going to be a 4+, and sulfide is, bring it back, is a 2- right there. So it's going to be OS, you need one of these to match up with 2 of these. So that's going to be -4, +4, and they balance. So it's OS and S2. Okay, and it's called osmium sulfide. You did not need to use a Roman numeral for osmium because it only has one charge state, and that's a +4. Okay, finally, these are some oddball elements that you hardly ever see. Yttrium is a 3+, and fluorine is a 1-. So we're going to put a 3+ times 1, 1- times 3 to balance out. That's a 3-, that's a 3+. All right, and that's going to be YF3, and it's yttrium fluoride. Okay, and that takes care of the ionic bonds and the names. All right, now we are going to draw some Lewis dot structures here. And all you need to do for these single elements is to draw just the Lewis dots for these single elements. So let me make a few corrections right away, and it actually comes down at the next section. This O should be O2. Okay, oxygen never exists as a lone atom. It's always paired with another oxygen atom to form an oxygen molecule. The PF2 should be PF3. And finally, the CN. We've talked about these in class, but let's be sure you get them down now. It's one of the advantages of watching these videos is if there's mistakes on the sheet, you can pick them up here. It's capital C, capital N, and then it's a negative ion. So we'll learn how to do that. Okay, let's get going. All we need to do is know the valence electrons for argon. So you just need your basic periodic table. Argon has, if you start on the left in the 3rd row, you count over, it's 8 valence electrons. It's a noble gas. It has 8. So you just start 1, 2, 3, 4. Now you start pairing up 5, 6, 7, 8. Okay, and that takes care of argon. Silicon, right here. It's got, count from the left. It has 1, 2, 3, 4 positions over. So it has 4. So you simply start 1, 2, 3, 4. All right, boron. Right here is 3rd from the left. 1, 2, 3. 3rd from the left in the 2nd row. So it's simply 1, 2, 3. Magnesium, Mg, right here is the 2nd element over in the 3rd row. So it's simply 1, 2. Again, starting at the bottom is just my convention, but you do have to space out the first 4 and then pair them up from the 5th one on. Okay, so remember that. Where you start is up to you, but I start at the bottom. Okay, tellurium is right here. Now, with these, let me zoom this out so you can see the whole periodic table, or somewhat close to it. Okay, anyway, tellurium is in the 5th row, so you only count the first 2 columns and the last 6 when you count valence orbitals. In other words, anything in the transition metal valley here does not count towards valence orbitals. So tellurium is in the 5th row, so it's 1, 2, then you skip over to indium, 3, 4, 5, 6. So it has 6 valence electrons. All right, so we have 1, 2, 3, 4, pair up, pair up. Okay, that's the valence, the configuration. And finally, barium. Barium is in the way down in the 6th row, but it's only the 2nd element over, so it has 2 valence electrons. 1, 2. All right. Move on to really the main part of this lesson, which is drawing Lewis dot structures for some simple molecules. You're going to learn a more thorough set of rules coming up here very shortly in the next week or so. But for right now, we're going to just learn some basic rules about how to draw molecules. So there's 2 rules to follow. The first one is 2 things that you have to accomplish when you do this. The first is you have to use all of the valence electrons. And the second rule is that all atoms must have a full octet. All right, and there are exceptions to rule number 2, but we're not going to get into those today. When we talk about this in more depth, we'll talk about those. Now, I'm going to recommend you do this on a piece of lined paper. While I gave you space here, in doing this myself, I kind of realized there wasn't quite enough space. So I'm going to do this on lined paper and just copy down each of the compounds here, or molecules. All right, so the first one, they're not numbered, but the first one is H2O. So what you need to do first is count the valence electrons. So for hydrogen, there are 2 hydrogens times 1. Each one has 1 valence electron. Then you come over here, and there it is right there. It's in the first column. It has 1 valence electron. That means there's a total of 2 there. And then oxygen, there's 1 oxygen atom. Each one has 6 valence electrons. And you come over here in your second row, 1, 2, 3, 4, 5, 6. 6 valence electrons. Okay, so you have a total of 2 plus 6 is 8 valence electrons. That means you have to have 8 dots on your paper when you finish drawing this. Now, we don't know any better, so we're going to say that the oxygen has to be in the middle. Hydrogen can never be a central atom because it can only bond on one side. So it has to be on the outside. Now, we're going to just say it's symmetrical, like this. Okay, so we'll draw it like that. That's not the proper drawing of water, but we're going to just assume that it is for our purposes. Now you need to create octets. So what you do is just create an octet around everything. Hydrogen could only hold 2 electrons, so there's an octet there. I'm going to go ahead and just create the octet around oxygen. So oxygen has 1, 2, 3, 4, 5, 6, 7, 8. That fills its valence orbital, which is the second orbital. Hydrogen's valence orbital is the first orbital, so it can only hold 2. And this one has 2, and this one has 2. So all 3 elements have fulfilled the octet rule. And as it turns out, we've used exactly the 8 electrons that we were given. So this is our diagram for water. Now actually water is at an angle and would usually be drawn like this, but you didn't know that. And until we learn about geometries of molecules, this would be perfectly acceptable to write it like that. But this is actually more correct. Okay, let's move on. Now we have CH4. Again, we have to count valence electrons. So carbon has, by the way, this is a colon, not a valence electron, so they kind of look the same. We have 1 carbon times 4 electrons, and again, where did you get that? You came over here, and you said 1, 2, 3, 4th element over in the second row, so that's going to be 4, and hydrogen is going to be 4 times 1 equals 4. So you have a total of 8 valence electrons again. Okay, we'll come over here. Well, CH4, again, hydrogen has to be on the outside, so we're going to just draw this symmetrically. We're going to put an H on each side. All right, and I should give myself, put space in between the letters so that you can place the electrons. Okay, so we're going to put an octet around carbon. 1, 2, 3, 4, 5, 6, 7, 8. So carbon has a full octet, and as you'll notice, the hydrogens all have full octets as well. 2 electrons is what hydrogen can hold, and we have a total of 1, 2, 3, 4, 5, 6, 7, 8. That's how many we had to work with. So that's our diagram for methane, CH4. All right, next up is ammonia, NH3. So we have nitrogen, we have 1 of those, and nitrogen has 1, 2, 3, 4, 5 valence electrons, 5th position over. Hydrogen, of course, there's 3 of those, and each one has 1 valence electron. So again, we're coming up with the number 8. It doesn't always happen, it just did in this case. Nitrogen has to be the central element, so I'm going to put H, 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 and H3. Doesn't matter which side, it just make it look symmetrical, somewhat even. We're going to put an octet around nitrogen. So nitrogen has an octet, each of the hydrogens has an octet, and we've used 8 electrons. So that's our diagram for ammonia. All right, next up is one of the corrections, and let me be sure those are made for you. There were 3 corrections. Let me go ahead and just do them right now. This should actually be O2. This PF2 should be PF3. And this CN is totally wrong. It should be capital C, capital N. That's carbon and nitrogen. And it should have a negative charge to it. That's going to add an electron to the diagram. That's cyanide, by the way. Okay, so it's capital C, capital N. Carbon, nitrogen. Okay, let's come on back. Let's do O2. Okay, so we have oxygen, we have 2 of those, and each one has 6 valence electrons. That's a total of 12. So they can only be drawn one way, really, and that's side by side. So we're going to create an octet around all of them, or both of them. There's 8 for that one. Okay, so there's 8, 9, 10, 11, 12, 13, 14. So we have too many. So the first thing you do is get rid of 2. And I usually just choose to get rid of 2 at the end, but you might choose somewhere else. But I choose to get rid of 2 at the end. Sometimes you want to get rid of, let's just save that for a later time. Okay, so now I have 12. I have 8, 9, 10, 11, 12. Okay, now this one doesn't have an octet. So at this point, since we have the right number of electrons, anything we erase, we have to put down somewhere else. So what do we want to do? Let's take this one off. And where are we going to put it? Well, we want to give that other oxygen an octet, so let's put it in the middle. And this oxygen now has an octet. There's 8 electrons right there. This oxygen has an octet because they share these 4. There's 8 electrons. We now have a total of 12, so that's our diagram for oxygen. Okay, next up is CO2. All right, so carbon. There's 1 of those. It has 4 valence electrons from your periodic table. That's 4. Oxygen. There's 2 of those. It has 6 valence. Each one has 6. That's a total of 12. When you add those, you get 16. So we need to end up with 16. Get on screen here. We need to end up with 16 electrons. Okay. Since there's 1 carbon and 2 oxygens, we're just going to assume the carbon goes in the middle and just assume it's linear. Like that. And now we're going to draw octets around everybody. So there's 1, 2, 3, 4, 5, 6, 7, 8 for carbon. And there's 2, 3, 4, 5, 6. So this oxygen has 8. Those two belong to that oxygen. And there's 1, 2, 3, 4, 5, 6. So how many total do we have now? We have 8, 9, 10, 11, 12, and 8 more is 20. We now have 20. So we have too many. Okay. So what I'm going to do is, what I always do is get rid of the ones on the end. Okay, now we do have the correct number. We have 8 on the carbon, 4 more here, 4 more here. That's a total of 16. We have the correct number, so anything we erase now we have to put down somewhere else. And these two oxygens, neither of them has an octet. So what we're going to do, and again, you just play around with this sometimes and you stumble into the answer. It's a little bit of creativity. But what you're going to do now is take those two from the top and put them over here. Take those two from the bottom and put them over here. Now, oxygen has an octet of those. Carbon has an octet of those. And this oxygen has an octet of those. Everyone has an octet, and we've used 16 electrons. So that's the correct diagram. And that actually is, carbon dioxide actually, unlike water, is a linear molecule. It forms a straight line like that. The oxygens are on opposite sides. So that is the answer for carbon dioxide rather. Okay, next is F2. That's fluorine. So we got an F. We have 2 of them times 7 equals 14. So we're going to just draw, it's just like O2, we're going to draw 2 Fs. We're going to create octets around them. And let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we've used the correct number of electrons, and everyone here has an octet. This fluorine has an octet. This fluorine has an octet. So that's it. We didn't have to make any double bonds or change anything around. It just naturally turned into an octet. All right. Moving down to the next row, we have C2H4. So we've got carbon, we have 2 of those times 4 valence electrons equals 8. Hydrogen, we have 4 of those times 1 valence electron equals 4, and that's 16. That's 12 rather, excuse me. There's 12, okay? So we need to end up with 12. So to draw this symmetrically, you may come up with something other than what I come up with, and there's a number of ways this could be drawn symmetrically. But the simplest probably is this. Put an H on the top here. On the bottom there, okay? And that actually is pretty close to what this ethylene molecule would look like. Not exactly, but kind of close. So now we're going to draw octets around the carbons. So let's count how many we have. Remember, these two belong to this guy as well. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have 2 too many. All right, so what you want to do right away is just get rid of 2 of them. And I usually do that at the ends. So now I have 12, but this carbon doesn't have an octet. It has 1, 2, 3, 4, 5, 6. So what I can only move some now. I can't, if I erase them, I have to put them down somewhere else. Well, what I want to do is take these 2 off the end and put them in the middle to create a double bond. We've learned that's the way we solve that trick. So this carbon has an octet right there, and this carbon has an octet right there. And of course, all the hydrogens have 2 electrons, so they have complete octets. So everybody's good. So that's what that molecule would look like. It has a double bond in the middle. Okay, next up we have silicon tetrachloride, and we'll get into the naming of these compounds. Covalently bonded compounds are named differently than ionic compounds, and we'll learn that in the near future. So it's SiCl4, so you have Si. One of those silicon has, let's count, 1, 2, it's in the 3rd row, 1, 2, 3, 4. So just like oxygen, it has 4 valence electrons. And chlorine, there's 4 of those, and they have, let's see, it's way down at the end, so it's in the third row. 1, 2, 3, 4, 5, 6, 7. It has 7 valence electrons. It's a lot. So now you have 28 there. The total's 32. It seems tricky, but it's really not. So the silicon logically would go in the middle. There's only one of those. So we have a Cl, 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 and Cl. Now let's build octets around everybody. Okay, we'll come over to this chlorine. Okay, so now it has 8 as well. This one has 8 as well. So if you look at this, the silicon has 8 around it. The chlorine has 8 because it shares these two with silicon. This chlorine has 8, it shares these two. This chlorine has 8, shares these two. This chlorine has 8, shares these two. So everybody has an octet. Well, let's count how many we have. Well, this is simple. It's 8, 8, 8, and 8. That's a total of 32. So we have used 32 electrons. Everyone has an octet, and there it is. Okay, just simple octets. Didn't have to change anything, didn't have to move anything for that one. Okay, all right, now we're going on to one of the ones that was corrected. That was PF3. So we have phosphorus, and phosphorus is right here. So it is the 1, 2, 3, 4, 5th element over. And there's one of those times 5 valence electrons. And fluorine, there's 3 of those times, and fluorine, where is that? It's way down here at the end, so if you count across 1, 2, 3, 4, 5, 6, 7, it's the 7th element over. That equals 21. So you add those two together, you're going to have 26 electrons on your page by the time it's over. So I'm going to put a P here, I'm going to put an F here, an F here, an F here. Okay, so PF3. Okay, let's just start drawing octets around everyone and see what we, where we start from as far as counting. Okay, let's see what we got. We have 8 around this one, 8 around this one, because these two count for that, and 8 around this one. That's 24, and then 25 and 26. So if you count those 1, 2, 3, 4, 5 all the way up, you'll end up with 26 dots, and everyone has an octet, as you can see. Draw a line between these two to make it clear. Everyone has an octet there, so we're good. That's the diagram for, it's called phosphorus trifluoride. Okay. And let's move on to Br2. So bromine, there's 2 of those. And they each have their halogens. So that means they have 7 valence electrons. Second from the end is going to be 7. Just count from the left, and you'll get that number. That's 14. So we got Br, Br, and we're going to draw octets. 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, because they share that. And so we have octets around both bromines. There's a total, if you count it, of 8, 9, 10, 11, 12, 13, 14, which is what we need. So this is our answer. We didn't need to change anything. Okay. All right, next up is SO2. Sulphur dioxide. And we got an S. We got 1 S times. Sulfur is the 6th element over, right there, second from the end, 6th element over from the left. So that gives us 6. And we have enough experience with oxygen. There's 2 of those to know that's also 6. So that equals 6. That equals 12. You add them up, you get 18. So let's put sulfur in the middle. O on the outside, kind of looks like carbon dioxide. Does have a different shape, but we're not there yet. And we're going to put octets around everybody. Okay, so this oxygen has an octet, octet, octet. These two belong to this oxygen here. Okay, so how many have we used? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so we've used two too many. So what I'm going to do is take off the end. Okay, now we have the right number, but this oxygen doesn't have an octet. So what I think I'm going to do is, okay, so now we've taken off one, so now we do have 6, or 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We have the correct number, but this one doesn't have an octet down here. So what do we do? Well, what we can do is this. If you take off this and put it there or there, that's not going to do it. It'll give this an octet, but this will lose its octet. So we somehow need to get some electrons here. So what you do is this. You have to take 2 off the sulfur. Now, how did you know that? You just kind of have to play with it sometimes. And it's like a little puzzle. And I'm going to put them right here. Now let's see if everybody has an octet. 1, 2, 3, 4, 5, 6, 7, 8. That oxygen has an octet. How about sulfur? 1, 2, 3, 4, 5, 6, 7, 8. That sulfur has an octet. And how about this oxygen? Well, yeah, there's its octet. So this is the diagram, but you'll notice something strange about it. It has a double bond between one of the sulfurs and oxygens and a single bond between the other. And that's called a resonance structure. It means you could have drawn the double bond over here instead of over here. It could have been on either side. So it means there's 2 different configurations of this molecule. We're not there to learning that yet, but that's how you would draw a sulfur dioxide molecule. All right, finally we have the last one, which is CN. It's the one I kind of left as a challenge problem in class. So carbon, there's one of those, times 4 valence electrons equals 4. Nitrogen, there's one of those, times 5 valence electrons equals 5. And whenever you hit an odd number of electrons, it's quirky, but it's a negatively charged. So there's an E minus, that's an electron. And that also contributes to the number. So now we have a nice even number of 10. So let's just draw the C and the N. It doesn't matter which side goes on which. And let's draw octets around them all. Okay, so this carbon has an octet, this nitrogen has an octet. How many electrons? Well, count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Turns out we used 14 electrons. So we need to get rid of some. So let's just get rid of the ones on the end. And now we have the proper number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But neither of these has an octet now. So what do we do? Well, we do what we did before. We're going to take a couple here. And we're going to put them in here. Okay. Now, this nitrogen now has an octet. It has 1, 2, 3, 4, 5, 6, 7, 8. But the carbon doesn't. So now what do? Well, we take a couple here. And we're also going to put those in the middle. So now this nitrogen has an octet, this carbon has an octet, so there you go, you have this bound. Now usually the way to draw this is like this. Usually put those lone pairs, those ones that are kind of out there by themselves on the ends. You don't have to, but that's usually the way it's drawn. And this is what's called a triple bond. Okay, we have single bonds, double bonds, triple bonds. There's nothing higher in terms of number of bonds than a triple bond in chemistry. It just doesn't exist, and you'll learn the reasons for that later on in this class. Okay, so that concludes this assignment, and that's due on Tuesday. Get it done tonight if you haven't done it already, and we'll see you in class.